Hello everyone, this is Puya. In this video, I'll talk about curve fitting. So this is a topic where you have a finite number of data points, and you want to see what happens in between those data points or like outside those data points, and you just basically want to have an approximation to find a function that would fit your data points. Um, so first, let's talk about interpolation. You have a given set of measurements. That's like what I call data points. It's sometimes useful to estimate values other than the one that you already have, right? Because like you want to basically do some experiments. The experiments are costly. You can't do it for infinite number of points. You have a finite set of measurements, right? And you want to approximate and you want to estimate values other than at the ones that you already have. So interpolation is the practice of estimating the values in between recorded data points. One way of doing this is to fit a curve to the data and use this for the estimation. So basically find a function that would approximate the behavior of your measurement or your data points, and using that function you can find the values in between the data points. Interpolation can be performed at different degrees, trading complexity for precision. So you basically can either use linear format, polynomial, quadratic, like power function, logarithmic function. You can use like different functions to approximate the behavior of your measurements. So you can like use a very simple function to do the estimation, right? Or you can use like a very complex function to do the estimation. There's a trade-off between, there's a compromise between complexity versus precision. Finding the best straight line that goes through data would mean like finding the values of A and B. So like you can basically approximate the behavior of your data points using a linear function, or you can just basically make it more complicated, make this function more complex, right? We're just like adding more terms, like making quadratic, or like basically increasing the order of this polynomial, right? This is like a very simple function. This is an example of curve fitting. Let's talk about polynomials. So polynomials of different degrees or orders can be used for interpolation. The degree of a polynomial is the integer of the highest exponent in the expression. For example, if you have a line, a straight line, this is a first order polynomial or a polynomial of degree 1. It's like the highest order exponent has the power 1, right? The exponent is of 1. A quadratic or a second order polynomial is given here. So this has degree 2. A cubic or third order polynomial is given here. So like that's what we meant by complexity, right? By complexity means like then you have like more coefficients to calculate. If you have a first order polynomial, that would be a line, you only have 2 coefficients to calculate. If you have a second order, you have 3 coefficients to calculate. A third order, you would have 4, and so on. As a review, I should mention that MATLAB represents a polynomial as a row vector of coefficients. If we have a polynomial like this, x cubed plus 2x squared plus 3x plus 4, you can represent it in MATLAB using the vector of coefficient. The coefficient for x cubed is 1. The coefficient for x squared is 2, and then we have 3, and then we have 4. So you can represent a polynomial in MATLAB using the vector of coefficients. You can also find the value of a polynomial at certain x values at certain points using the polyval function. This is short for value of polynomial. So it takes two parameters, like the vector of coefficients of your polynomial, right? This is how you present a polynomial, and these are the points, the x values that you want to find the value of this polynomial at. So basically replacing 2 for x in this polynomial and finding the value of the polynomial, and doing it again for 3, finding the value of this polynomial. You can also find the roots of a polynomial using the roots function. And the roots basically are the values of x that forces the y or our function to become 0. It's like the zero crossing of your function. The roots of a given polynomial p can be obtained with the command r equal to roots p, where p is the vector of coefficient. So here this is like a third order polynomial, so it would have 3 complex roots, right? So like these are given here, right? So like using the roots function, you can find all the roots of the polynomial. You can do the reverse process, like if you have the roots and you want to find the polynomial, you can use the poly function, that you provide the roots and the poly function would give you the vector of coefficients. So if I provide this vector of roots to the poly function, it would give me the vector of coefficients for my polynomial. There is a technical difference between interpolation versus regression. Sometimes they are used interchangeably, but there is a technical difference between them. Regression is the process of finding a curve of best fit, measuring and minimizing in a given metric prediction of a data value and the observed data value. A regression fit does not generally pass through the data points. Right, so you have certain data points and you want to find an estimation, or you want to find a function that mimics the behavior of this data points. The regression fit does not necessarily go through all the data points, or does not necessarily go through any of them. It just basically, it's an approximation. Define an appropriate metric, we can perform regression on any set of points with any polynomial of any grade, right? So this is what we're going to use for curve fitting. This is like the regression, right? That's why like when we find the function, it like does not necessarily go through any of our data points. It just like it estimates or approximates the behavior of our data points using approximate metric, using a criteria. Like our criteria is usually the least square criteria. Okay. The interpolation is finding an approximation of a function y equal to fx defined by the discrete set of values x and y's, like these are our measurements or data points. And the interpolation fit traverses through all the available data points that we have, right, while guessing the value of unknown points, right? So this is the difference between interpolation and regression. Basically, regression does not generally pass through the data points, but interpolation does. Okay. However, like the application of interpolation would be limited. If you have a set of n values for the function y equal to fx, we can interpolate them with a polynomial of order bigger than or equal n minus 1, right? So like let's say like if you have 3 points, can we interpolate them using a line? Not necessarily, because those 3 points are not gonna, like most probably they're not gonna fit on the same line. If we have 2 points, yes, we can, right? If we have 3 points, then we need like a quadratic function to interpolate the behavior of those 3 points. Okay, so that's the difference between interpolation and regression. And in curve fitting, we use regression. So our our function that's going to fit the data, it's not necessarily going to go through any of the data points that we have. Right, so this basically shows here, right? Like if we have 1, 2, 3, 4, 5 data points, we can't find like a linear interpolation, right? Because it's not going to be possible for these 5 data points to be on the same line. Like if you have 2, yes, it is possible, but if I have 5, we can't find a line that goes through them. But you can do a regression, right? A linear regression. It's not going to be a very accurate, precise, care fitting, right? But you can find a line just that basically goes, like it doesn't go through any of these data points, but can just like find the like it would have the minimum error compared to any other line that would approximate the behavior of these data points. What is the criteria that we use for regression? We use least square criteria. We try to minimize the error. We try to minimize the distance of the line or any other function that we're going to use for fitting. We're going to minimize the distance of every point from that function. Okay, so we use the least square criteria. I'm going to show you again what the least square criteria is. This is like introduction to some functions in MATLAB. Inter-P1Q. It can be used to basically find the line that goes through some data points. Like here we only have 2 data points, the ones that are filled, like these are our data points, right? And using Inter-P1Q, we can find the line that connects them together, right? It's a simple task to do. We can do it ourselves, but there is a function that does it, right? So it basically returns the, like if we have our data points x and y's, and then we want to find the value of this line that connects the data points at other x values, right? You can use the enter p1q. There is a similar function called enter p1, right? So that can also be used to do that. It basically returns the interpolated value of one-dimensional function at a specific query points, right? So these are our data values, but we want to find the function values at other things. And like here you see that like it uses piecewise linear approximation, because like if these are our data points, we can't find just one line that connects all of them, that goes through all of them, right? So we use this function uses piecewise linear approximation or linear interpolation. It would just like connect every 2 points using a line, and using these multiple lines you can find the value of y's for other query points. Now let's talk about care fitting or regression. So again, we have certain data points, right? And we want to find a function that would mimic or estimate or approximate or simulate the behavior of these data points. It does not necessarily go through any of the data points, right? And we can use different functions with different orders or different degrees to do this approximation. So in this example, we're going to use a polynomial of order 1. So it's going to be a line, okay? So to approximate the behavior of these data points, we see that like this line does not necessarily go through any of these points. But what is the special property of this line compared to any other line that we can have? The special property of this fitting line would be that it would have the minimum error. How do we find the minimum error? The minimum error would be calculated based on the least square criteria. So for any x's, right, for any x value of these data points, we have 2 y's. One is the y of our data value, our measurement, and one is the y of this at this line, right? So if we find all these differences, like y1 minus, let's call it y hat 1, y2 minus y2 hat 1, y3 minus y hat 1, if we raise this difference to power 2 to get rid of the negative sign, because like this difference, it doesn't matter if it's positive or negative, we only want to look at the absolute value of it. And if we sum them up, right, the curve fitting provides the best line that mimics the behavior of these data points based on the least square criteria. It would basically minimizes the area of these squares, right? So like this is like y1 minus y hat 1, y2 minus y hat 1. If we raise them to power 2, would be the area of these blue squares, right? So that's what the least square criteria is. And in our curve fitting, we use this criteria to find the best fit. It doesn't matter if it's a first order polynomial, second order polynomial, third order polynomial. For each of these order polynomials, we use the least square criteria to find the best version, the best line, or the best quadratic curve, or the best third order polynomial, and etc. So this is an example, right? We have a set of measurements, right? So like these are like price of houses in a certain part of this country, like where housing is cheaper. So like based on a square feet, you would have the prices. This is definitely not Vancouver. This is definitely not Vancouver. Not nowhere in BC. Maybe Nova Scotia or like Manitoba, right? So then we want to figure out, like we have different square feet, and let's say like we want to find the like what is like the approximate price of a house with 1200 square feet, right? It's not like available in any of our data points, right? So one way of doing it is using curve fitting. Now we have many different options for curve fitting. Let's say that we want to use the very simple one, right? We use the first order polynomial. You can use the polyfit function that does the curve fitting for polynomials. It basically fits or does the regression on certain data points that we have, right? So here this is our vector of x, this is our vector of y. We provide it to the polyfit function. We also have to determine what is the order of our polynomial. And then the polyfit function gives us two numbers. What are these two numbers? These are the coefficients, the vector of coefficients for our polynomial, right? Because we have a first order polynomial, because we determined that we want to have a first order curve fitting, we only have two coefficients, because in a line you only have, like, let's say ax plus b, you only have two coefficients, right? So this is going to give us the line that would fit these data points, right? And this line would be the best fit based on the least square criteria. The polyfit would give us the least square criteria fitting, right? Then once we have the function that would mimic this, that would fit this data, then like you can just basically put any x in this function formula, in this line expression, and find the y for example for x equal to 1200, right? Or for x equal to like 2000, right? You can find the approximate price of this house with this much square feet. You can also do it yourself, right? So like let's say that you want to find the best line that goes through like certain data points, like using regression, like not necessarily going through any of the data points, like the best line that fits the data points. So if we have the formula of the line like this, it would have two coefficients. So we basically have to find these two coefficients. The polyfit function would give us the coefficients, right? You can also calculate it yourself using these formulas, right? So like that's basically how polyfit function would find a formula, right? So like this is basically minimizing the distance between the y value of the lines and the y's of our data points. The n in the polyfit function, which is the order of the polynomial, can be any number. So you can increase this, right? If you increase this, you would have a more complex fitting function. You would have more coefficients, right? So for a line, you would only have 2 coefficients. For a quadratic curve, you would have 3 coefficients. For third order polynomial, you would have 4 coefficients, and etc. Like it would increase, right? As your complexity increases, right, your accuracy is going to be also increasing, right? Let's say like these are our data points, these circles that we have here. Okay, if you have a line, let's say like I don't know which one is the line, probably the red one maybe, like one of these red, green, or yellow ones, right? So here, this, like, I should have provided the legend here. Like, I'm sorry, this like doesn't have a legend, but like here, this shows different curve fitting, like from order of grade 1, or like order 1, which is a line, it goes all the way to order 6, right? Because we have 7 data points. If you have 7 data points, you can find a unique 6th order polynomial that goes through all of these data points, which is the I think it's the light blue curve. You see that the light blue curve goes through all of them, right? So this one, like, it basically goes through all of them. So like this is the 6th order polynomial that would, this is interpolation, that like basically interpolates all these lines, all these data points. The first order polynomial, it's the best line that would fit the data, but it's not very accurate. As you increase the order of the fitting, right, you get closer to your data points. You see like 1, 2, 3, and then 4, 5, right? Like for the dark blue one, like it's going through most of the data points, and like the distance from the others, like it's minimized for that order of the polynomial. If you go up to the 6th order polynomial, then it goes through all of our data points. Okay, if you have n data points, you can find an n minus 1 order polynomial that goes through all the data points. So like that's the limitation for interpolation. So this is a function that would do the linear curve fitting based on the formulas I provided here, right? So it should give you the exact same numbers that the polyfit function gives you. You see that like here, like it gives us exact same coefficients, right? So like you can either calculate it yourself or use like simply the polyfit function. This is another example. We have like data points that are given here in red circles, and you see like here, like this is the first order curve fitting, the second order curve fitting, and a third order curve fitting. So you see that it like this is a trade-off between complexity and precision. This is very simple, right? It's not as precise. This is getting better, but it's like more complex, and then like it gets even more complex, and it gets more precise as well. So using polyfit, you can fit the data, and then you can find the value of this polynomial at other points, like in between your data points, or even outside your data points, using the polyval function. This is an example for you. We have set of measurements or set of data points, and this is asking you to provide a plot for first through fourth degree polynomials. So basically doing the same thing that we did here, but on different set of data. So the polynomial care fitting is very simple. We just like use the polyfit function, and it basically minimizes the summation of um, the errors, the squared errors, right? So it minimizes. That's why like it's called least square criteria. Okay, but sometimes we know that the fitting function is not like based on our like other information that we have about the problem. Let's say like this is a physical problem, like it's an engineering problem, and we already know that like the relationship between y and x should be of certain format, right? We just don't have the coefficients, right? It might be an exponential, it might be a power function, it might be a saturation growth rate function, something like this, right? We know that the behavior should be like this, but we don't have the coefficients, right? And we want to find the coefficients. Now, none of these are like in the standard format of a polynomial, right? What if I want to find the best exponential function that goes through these data points, or like the best power function, or the best saturation growth rate function that goes through our data points? So if that's the case, we just have to do some manipulation of the data. Like we have to try to these are non-linear functions. We have to basically using some variable change and some mathematical manipulation, we have to turn these non-linear expressions into a linearized expression, right? So for this one, if you take log of both side of the equality, the left hand side and the right hand side, and like it makes sense to take the log in base e, the natural log, because here like we have e raised to power beta 1x, right? So if you take the natural log of both sides, you would have natural log of y on the left hand side. Log of a times b would be log of a plus b, right? So you would have natural log of a1 plus natural log of e raised to power beta 1x, right? And the log of x to power alpha is alpha times log x, right? So like these are like very simple log formulas that you hopefully remember from previous math courses. So like if you do that, a natural log of e is 1, right? So that's what the natural number, the Neper number is, right? So then if we take natural log of both sides, this equation, it's going to be transformed into this equation. Now if you look at it, if I call this one, if I do a change of variable, and let's say like if I call this ln of 1 natural log of y, like let's say I call it capital Y. If I do that, then this is a linear function. This is a linear function, right? And using polyfit, I can find alpha 1, actually can find like log of alpha 1 and then beta 1, right? And then if I have log of alpha 1, I can also calculate alpha 1. So you can find like alpha 1 and beta 1. So first, we have to do some manipulation to convert our curve into a linear curve, and then we can find the coefficients. We might have to do some, again, like some manipulations to find alpha 1 and beta 1, because in this case, if you apply polyfit on x and logs of y, it would give you natural log of alpha 1 and beta 1. And to find alpha 1, you have to do a power. Like you just like basically have to like raise this number, raise e to this number to get alpha 1. The same thing for a power function. If you have a function like this and we want to find the best power function that fit our data, this is not a polynomial, it's missing some terms, it only has like one term of a polynomial, right? Or like maybe like even like beta 2 might not be an integer number, or like a positive integer number. So like in that case, right, again, like we have to do some manipulation to turn this non-linear function into a linear one. How can we do that? We can take log of both sides. In this case, it doesn't matter like what the base is, right? So like it can be natural log or log 10, even log 2. It just like so here like we take log 10, it's like easier to calculate. So on the left hand side we have log of y. On the right hand side we would have log of alpha 2 plus beta 2 times log of x, right? So then if we like, you see that this is like, if I call this one capital Y and if I call log s capital X, would have a linear relationship between capital Y and capital X, right? So then I can apply linear curve fitting on this function, and then I can calculate log of alpha 2 and beta 2 using the polyfit log x log y comma 1, and then based on that you can then calculate alpha 2. The same thing for this one, right? Using some manipulation, so basically inversing both sides, we end up with this function. Again, you can rename this one as capital Y. You can rename inverse of x as capital X, right? And then again, you have a linear relationship between capital Y and capital X. So you can calculate the coefficients. This time the coefficients are going to be 1 over alpha 3 and beta 3 over alpha 3. Once you have these coefficients, you can actually calculate alpha 3 and beta 3. So this is basically what's going to happen. Like if we have an exponential function, right, y versus x has exponential behavior, but in that case natural log of y versus x would have a linear relationship. If y versus x has a power relationship, then log y versus log x would have a linear relationship. If you have a saturation growth curve relationship between y and x, 1 over y and 1 over x, they would have a linear relationship. We can find the slope and the intercept of these lines using the polyfit, the order of 1, right? Because these are lines, these are first order polynomials, right? You can calculate the slope and intercept. After doing that, then we can find alpha 1 and beta 1, or we can find alpha 2 and beta 2. We can find alpha 3 and beta 3. So this basically like shows you that like if you have a linear function, it would have a straight line. For a power function like this, right, if we have a log axis right here, like if you have a log axis, we end up with a straight line, right? So like if our curve is expressed in terms of log y versus log x, we would have a straight line. So this is like the manipulation or the linearization that we have to do. The same thing for exponential function, right? You see like the base can be e or it can be any other number, right? So if this is the case, it makes sense to take instead of natural log, take log in base 10, right? Because then like this would turn into a very nice linear format. Like if this is the case, we take the log in base and the natural base. Okay, so this basically shows like how you can linearize different functions. Okay, so what you have to do, right, if you have a function like this and you want to find the best b and m that fit your data, right, we take like here, like we take log of both sides, right? Remember that in MATLAB, if you just write log, it would be natural log. If you want to log in base 10, you have to write log 10. So here, like it doesn't actually matter what kind of log you have to do. Like then, like you just like your corresponding operations is going to change based on that. But here, if we take log 10 of both sides, then we would have an equation like this, right? By renaming this one as W and renaming this one, renaming this one, let's say, as W, and renaming this one as Z, right? Then we have a linear relationship between W and Z, right? Where P1, it's going to be the slope of the line, which is the same as M that we wanted to find, and P2 is log 10 of B, right? So then you just like basically apply polyfit on W's and Z's, or Z's and W's, log 10 of X and log 10 of Y with the order 1. You find P1 and P2. Your P1 is the same as the M that you were looking for, but your P2 is log 10 of B. So in order to find B, you just like have to like basically have 10 raised to power P2, because if P2 is equal to log 10 of B, B is going to be 10 raised to power P2. The same thing for this function, which is a power function, exponential function, right? If the number is 10, it makes sense to take the log again in base 10. If this was E, we would take the log in natural base, like base E. So again, we do the same thing, and like this is going to be simplified this time. Like again, change of variables, we call this one W, right? It actually didn't need to change the name of X here to Z. Z is the same as X here, right? This is like a semi-log curve now, right? So like in this case, again, we have a linear relationship between logs of Y and X, right? Where P1 is the same M that we are looking for, and P2 is log 10 of B, right? And again, you can just apply polyfit on X and log 10 of the data points that you have, log 10 of Y's of the data points that you have, right? It would give you the P1 and P2. The P1 is the same as your M that you were looking for, and P2 is log 10 of the B that you were looking for. So you can find B using this formula, right? The same thing it's going to apply if we have the saturation growth curve, right? The only difference is that your change of variables is going to be like you call 1 over Y, the like W, and 1 over X, the Z, right? So like again, you apply polyfit on 1 over X and 1 over Y, and then find the coefficient, and based on that you can find the the actual coefficients, like here alpha 3 and beta 3 that you were looking for. So I have an exercise for you here, right? So we have a set of data points. We actually have 20 data points, right? We have 20 data points, and I want you to find the best line, the best quadratic function, the best third order polynomial, the best exponential function when like the base is E, like when the base is 10, or the best power function, right? That would fit these data, right? So like here, like you have to find A and B, A, B, C, A, B, C, D. Here, A and M, A and M, A and M, right? Once you do that, also want you to tell me, like, out of these 6 different curve fitting function that you found, which one would be the best one? Which one would be the best one? We know that we found the best line, the best quadratic curve, the best power function, right? The best exponential function. But out of these categories, which one would fit the data best? How can you do that? What is the criteria to measure that? Again, you can use the residual vector, right? So you can find the actual value of your data point at these x's that you have here are x's time, right? So you actually can find the actual value of the data points at those x's, and the values that the curve fitting functions would give you for those x's, right? And then find the error, and you can use the least square criteria for the error, right? So like find the error function, the residual vector, and see for which one that error is minimum. In some cases, we might need to again like do some manipulation on the data points that we have, right? So we might have to scale the data or shift the data. So the effect of computational errors in computing the coefficients can be lessened by properly scaling the x values. You can scale the data yourself before using polyfit. Some common scaling methods are like subtracting something from the x, or like minimum the value of x. You can subtract the minimum value of x from your x values, or divide the x by something, by the maximum value, just like basically finding the per unit value, right? So these are some scaling values. As an example here, you would have like these are your x values, these are your y values. You see that like here, like your x values goes from 2007 all the way to 2016. They're like concentrated or clustered around like just like a very small part of the x-axis, right? So like a very good scaling of this data would be just like renaming or like a change of the variables, where like you change x as year minus 2007, like which is the minimum value that you have, and then apply the polyfit, right? So you can do the polyfit again like in the original data, but it's not gonna give you like a very precise care fitting. So this is like a better option, that a better solution that you have, like first scale the data, right, and then apply the care fitting. The same thing here, so like here you have some like data points, right? So like this is like the time, this is the temperature, like you have these data points, and you know that the relationship between temperature and time should be something like this, right? So like you want to find, sorry, it should be something like this, right? Something like, so it's basically an exponential function, right? You want to find the best b and m, right, where lowercase t is time and capital T is the temperature, right? But here you see that it would be better first to just rename the variable, like having your temperature minus 68 and using that variable in your polyfit, and then you can apply the what we did for the exponential functions to find the best b and m. Like here, like it shows you the process of doing that. This is an exercise for you. Please work on it yourself. Thank you so much. These are the references for parts of the slides. Thank you so much. Stay tuned for the next slide, the next video.